And if we look at it, we calculated the my video is not on. Okay. And if we look at it, this is the same acceleration that we got last time when the force was completely in the horizontal direction. All right. So, and here we're applying FP is the same. FP is 40 newtons. Last time we also applied 40 newtons. So at this particular, whenever it's 0 or 30 in this particular problem, the acceleration in the x direction will be the same, right? Because in one case, you're applying more force in this direction, and you compensated for a larger force of friction. But when we apply an angle, we reduce this force of friction, but we also reduce the force going in the x direction. So there's a compensation between the two. And you can optimize this problem to get the correct angle, right? So how would we optimize it? All right. We would have A in terms of theta, right? If we wanted to optimize this, we have A in terms of theta. We'll take to maximize A, right? We set the derivative equal to 0, right? And then we can find the maximum, the best angle for the maximum, to have the maximum acceleration. Check out example 5.4 at home. Is it better to push or pull a sled based on force diagrams? And so it's an interesting one. Let's see, what should we do next? Please check out example 5.5 and 5.6 at home. And we'll do 5.7 right now. By 7. In this problem, we have two masses connected to each other by a piece of rope. And one mass is hanging off the side of an inclined plane, while the other one is on the hypotenuse of that plane. And then you have an angle of 37 degrees. MA is equal to 10 kilograms. MB is what we're going to look at, right? So the problem asks for if the coefficient of static friction is 0.40. What are the ranges of values for mass? To keep what are the ranges for mass B to keep the system at rest? So this it's asking you for the range of values to keep acceleration 0, right? And there's going to be a range because within the static coefficient of friction, as long as the coefficient of friction is greater than any of these forces in this direction, it will not move, right? And let's take a look at it. So if we start off with 0 mass over here, right, what happens? The box slides down this way, right? And then so in that case, in case 1, we have this. All right. For case 1, we'll have we have our normal force, we have a force due to gravity, and then if this is 0, that means that it's going to be sliding down this way, and that implies that the force of friction is going the opposite way. And then if there's some weight on here, the tension force is going in the same direction, right? So I have 2, the tension force and the friction going in the same direction, and this will counteract the acceleration due to gravity downward, right? In the case that MB causes a force larger than the force of friction, now if MB is large, it would pull the second block up and it will accelerate in the opposite direction, right? I'm just going to write MB is large, right? In this case, right, the box All right. Be like this. We have the Fn. Then we have gravity. Mg. And then in this case, since it's moving upwards, the force of friction is in the same direction as gravity, and then we have the force of the tension, which of course is going to be larger. Okay. And then for mass, so these are the two free body diagrams for a mass A, right? In these two cases, where it's sliding upwards, the other where it's sliding downwards. The free body diagram for mass B is only in one case, right? There's only two forces on here. There's the tension force, and there's the force due to gravity. Right? So these are our two cases, right? And we're looking for the case where this box is no longer moving, right? So what values of MB would occur where it's small enough to stop it from falling downwards, but not large enough to make the box move up the slope, and that's what it's asking for, right? So let's write down the equations of motion for this. All right, I'm going to erase this stuff. So X. So we have to set up our coordinate axis. We'll take our coordinates like this, right? Well, this direction we'll call Y, this direction X. And let's solve our equations of motion for A, right? MA from SA. So in the Y direction, right? So we have so for the Y direction, for both will be the same, right? And this would be my, which is 0 for the, and we would have the normal force minus mg in that direction. If we look, right, it's this angle, which implies that it would be this angle. It's that angle, so then we would have to deal, if we're looking at it for the y, that would be cosine mg, right? This would be cosine mg, because this is the angle. You can see it as we raise up. The direction of mg changes from the vertical, from the y direction accordingly. So then we know that the normal force is this. And this is for both cases, case 1, case 2. Now, in the x direction, that's where things change because of this frictional force. All right. So let's find that. Case 1, or case 1, right? The x would be max is equal to, let's do this. So case 1 is where it's about to move downwards. So it would be Ft plus the force of friction minus the component of gravity in that direction, in the what we call the x direction. All right. Now let's plug in our values for this. Where do we get Ft from? What is Ft? Anybody tell me?
What's the tension?
What? The tension, yes. And how do we calculate? What equation do we use to calculate that with? So we'll use mass B, right? The free body diagram of mass B. So what's the force equation for mass B? We'll write it at the top. Right, it's this the acceleration in this direction, right, is equal to T minus the force due to gravity, right? Just that. So that means that Ft is equal to the force due to gravity. Well, if we're assuming that it's not moving, right? We're looking for this area where this block is not moving, so that implies that Ft is equal to m to the force due to gravity, which is equal to mbg. So the tension force is the mass b times gravity, right? The acceleration due to gravity. So that's where we get Ft from. Ff is just Ff is just the normal force times the coefficient of friction. Static times Fn, which is right over here, mg cosine theta minus mg sine theta. All right. Now, of course, these AMs are all A's right over here. Okay. Now we have this equation, right? And the smallest value that MB would be to keep everything in its static position is given when this is 0, when the acceleration is 0, right? So we would have this. Right. And then if we're finding the mass, we bring that over. right? And then we can divide by G out on both sides. And we're left with this. And then these two G's cancel out. And then when we plug in the numbers, mu here is 0.4. We plug in the numbers for the problem, we get 2.8 kilograms. So what is this saying again? This is saying that when we have a mass of 2.8 kilograms, that will just stop it from sliding downwards this way. Anything lighter, it will start to accelerate down. Mass A will start to accelerate down the incline, and mass B would go up in the vertical direction. Yeah, right? So that's one limit. The next limit we want to find is just when mass B is just large enough where if we add any more mass to it, it would start to move upwards instead, and pull this mass upwards. That's the next situation we want to find. We want to find exactly when the force due to mass B will overtake the static coefficient of friction, right? And we'll use this case to find that relationship, right? It's in this case, when A is 0, that we'll find that particular problem. And the first case was when mass B was just large enough to stop it from sliding back down. So in case 2, let's update it for case 2. In case 2, it'll start moving backwards. So that means the force of friction is in the opposite direction, is in the negative direction now. And we'll just update this, change to case 2, and we'll just update this quarterly. So instead of a positive, we have a negative here, and now it's case 2. I change it down here. It's also a negative. And we'll change it right over here, a negative, right? And then this would be 2 positives, would be positive now, right? And that's the major difference, right? It's just the sign. It's the only difference between the two cases is the direction of friction, right? And they'll give us a completely different answer. Now we have this. So now if we plug in all these numbers, we find that mass B in the second case will be 9.8 kg. So that means for this mass to stay stationary, mass B has to be between 2.8 and 9.2, right? Now in part B, what it asks for is if mass 2, so let's erase. if mass 2 is 10 kilograms and the coefficient of kinetic friction is 0.3, what is the acceleration, right? And if you look at it, which case would this be? This is where MB is larger than the static case, so that means we're dealing with case 2, right? Now it's asking for the acceleration. So let's write down the force equation and this in the x direction, right? And then we'll just write it down. And then we just solve for the acceleration. Right, and we got this equation over here. And when we plug in the numbers, well, and then, so that's for A. I'm sorry, I missed something. Okay, so got to do the tension force. So this is equal to the tension force. Because now it's moving, the tension force is in mg, right? It's ma-ax with fg minus ft, all right? Now we find ft to be fg minus bax, right? And then this is just equal to, right? Because it's accelerating downwards, there's not as much tension on this rope, right? So this is the tension, the new tension force. We'll plug it into this. And let me just rewrite this a little bit. So I brought this over to the other side, and then we're left with the same equation that we had originally. Right. And then when we solve, we'll solve for this. And then this is divided by MA. And that's it. Yes.
Where'd you get the on the bottom left? Where'd you get the MAG?
This
MA.
one?
Yeah, sine theta.
Oh, so this MAG sine theta is the force due to gravity in this direction. Right. So I just erased the free body diagram. So we're just summing all the forces in this x direction, right? And we have mg this way. So that means that part of mg is in this direction. And
Wouldn't that be cosine or?
No, it would be sine, because this angle relative to the incline over here, this is what's usually given to us.
Yeah.
Angle translates to this angle.
Okay, but wouldn't that be the y direction though?
What? No, sine theta would be this direction. Now, let me draw a little bit bigger. Let me do this. This is important to know. So these are two coordinate axes, right? This is y, and this is x, right? And this is our angle, right? So in this case, gravity is pointing downwards, right?
Yep.
If you look at this angle, right? So as I'm applying this incline, right? I'm moving it up. What happens? So if there's no incline, mg is totally in the y direction, right?
Yeah.
As I lift it up, it makes more of an angle with respect to the y-axis, right?
Yeah.
As I lift this up, this angle with the y-axis is the same as this angle with the incline. So when you're given the angle for the incline, that implies an angle relative to the y-axis, right?
Yeah, and that's what I'm asking. Because we're doing the x-axis, we're not doing the y, right?
That's correct. But in this case, now in the previous problems, what's normally given to you for like projectile motion is the angle relative to the x-axis. So normally when you do a problem, you're given this angle.
Yeah.
You see that? You're normally given this angle. And in this case, this would be cosine. Right? Let's say if we have a vector A, right? We have a vector A right over here. Our x component is given by A cosine because x is the one is the component that's adjacent to the angle. You see that? Over here, we're given the angle to the y-axis, which means that the component to the x-axis is now sine.
Oh, okay.
So instead of this angle, we're given this angle. You see that? And in this case, this would, and in this case, that component would be a sine theta. You see that? So that's why we're using sine theta over here.
Okay, makes sense. Makes sense.
Yeah. So this is all dependent on what angle you're given in the problem. So you can't assume that cosine always goes with x. You have to decide. You have to figure out which angle of this triangle you're looking at and which leg you want. Right. So for this particular problem, it's easier to do it this way. So. All right. Oh yes. So then this is the acceleration, right, for this problem. Once the mass gets heavy enough, and then we find that the acceleration, if we actually measure it, comes out to be. So in these problems, what we're doing is that we're figuring out the forces for all the objects in the system, right? In both directions, x and y, and then we're relating them to each other to solve some unknowns, right? We had this unknown, right? Ft. So we looked at the force diagram on V, and we were able to find Ft from there and plug it back into our original problem, right? And the same thing with the normal force. We use the forces in the y direction to figure out the normal force so that we can figure out the coefficient of friction. Any questions on friction? So, anybody?
I think I'm good.
Okay. All right, so we'll move on to circular motion next. We'll return in 10 minutes, and then we'll finish the rest of the chapter. Okay.